All right, number 54, for the alkaline Lalande cell, write the overall cell reaction. Determine E naught of the cell for that reaction.
Page 888.
Is it 888?
Oh, the zinc one?
Yeah, there's one here. And so to write the net reaction, we just add up all the half reactions here. And so the anode half reaction, zinc goes to Zn2 plus 2 electrons. The cathode half reaction is this. But it turns out the electrolyte also reacts. It has ammonium and hydroxide in there. And the way the electrolyte reacts is as the hydroxide is being produced, the ammonium neutralizes it here and converts it to ammonia and water. And then the ammonia reacts with the zinc 2 plus and the chlorides and precipitates it out. And so what we do is we add up these 4 reactions together.
In the solutions manual, they only did 2. They only did 2 reactions.
Well,
The oxidation and the reduction.
they only added the oxidation and reduction?
Yes.
Okay, that's because E naught of the cell, when we do this reaction, it's going to change. You know, delta G changes. When we add up this reaction, delta G changes. And so what they're doing is they simplified it because they didn't give you what the delta G's for these are.
But couldn't we find it in Appendix D
Um,
and convert all of them to
yeah,
voltage?
possibly. And so what we do is we'll just assume that, you know, these, even though these do contribute, we'll assume that these don't really change the potential. It would change the potential because you're forming more stable products,
Yeah.
and so you'd expect the potential to increase. But, you know, we'll just use, because we have the numbers for these in the book, we'll just use those.
I know, but some, like, they would say that we need K equilibrium. What is that? We already have the numbers. Why do we need K equilibrium?
Well, we need K equilibrium for the net reaction. You know, after you add up these 4, we get the total reaction, and then
Yes.
we need K equilibrium. And then from K equilibrium, we can figure out what delta G naught is, because delta G naught is equal to minus RT ln of K. Okay. And so that's another way. But we don't have the information on these 2 reactions, so the best we can do is just add up these 2 and
And that's
say
it?
it's going to be close to that. Yeah, because this is where the redox is happening. This is an acid base, Bronsted.
Yeah.
This is a combination of Lewis acid base and metathesis.
So do we use kind of like KF for
Yeah,
that?
we don't have the driving forces. I mean, we could use KF, we could use that, but you know, what do we do about the precipitation reaction and that? So since we're missing the data on those 2 reactions, we can just say that this is going to be close, but not exact, you know? Because the bulk of the pulling from the electrons is going to come from here, and then just forming more stable product is just going to help it. That's all. So, you know, ballpark figure for the E naught of the cell would just be those 2 reactions. Okay?
Okay, but I saw they do much more than that. Do we do much more than that?
What was the much more that they did?
Like they define the K equilibrium. I mean, why would we find the K equilibrium if we have those numbers already?
Let's see. Write the overall cell reaction. We'll just add them up. Determine E naught for the cell. We don't need to determine K equilibrium for that if we have the half potentials. But the problem is do we have the half potentials? And so let's go back to see what the data is given. Well, I need to look. This one is in the table, right? Zinc
Yes.
goes to Zn2 plus. But is this one in the table?
No.
No. That one is not in the table.
So you got to use delta G.
Right. if MnO2 and Mn2O3 are in appendix D, are they in appendix D? And so let's go take a look at appendix D. Oops. And so we're going to M.
No,
We have MnO2 here.
but not MnO3.
We don't have Mn2O3, unless it's in another part. So let's take a look.
That complicates things.
Right, and so either they're going to have to give us some.
Oh, there is. It's there.
Is it there?
Wait, where?
Just kidding. I'm sorry.
No!
I'm sorry. There's one above it, and I thought it was.
Unless they gave us the potential earlier. Let's take a look.
I mean, like, we're given one, but not the other. I mean, it's MnO2, but not Mn2O3. I guess we gotta use
You don't
double
eat
U.
it though, right? You don't eat it. Because you just use the formula to find food K.
Yeah, and so we have to look for the data. There's got to be some additional data there that we can look up and then calculate it. So we have to figure out what.
I just know Mn2O3. Then what do we do?
You can't do much, unfortunately. There. The only thing you could do is to look. In fact, I can't scroll down, but you'd have to look around.
Right here or appendix D?
In either in the chapter or in appendix D. Let's see. What else is given?
Is there a standard voltage?
Does it give you the standard voltage somewhere for that cell?
That's how the solution manual did it. They had the standard voltage, and then from that they were able to just.
Well, we have the voltage here, 1.55 volts. But what are they using?
0.93.
0.93 for which electrode? Mn2O3?
Yeah. No, they put standard voltage is plus 0.93 at 25 Celsius.
All right. Well, it's got to be somewhere in here, you know. Otherwise, you can't solve it unless they give you the data.
But you wouldn't give us a problem with this, right? You'll give us-
No, you'd have. Yeah, I'd give you a problem with the data, so you don't have to worry about it too much. So don't worry about it. Mhm.
So, sorry, was that, were you done with that?
Yeah, don't worry about it too much.
Okay.
Professor, is glow battery rechargeable?
No, not really.
Just a secondary, right?
Yeah, secondary batteries rechargeable.
Oh, so, for the practice exam, number 18, there's two, but the one before that, it's asking what is N? Is N and Z the same thing? Is it the number of moles of electrons?
Excuse me, I asked that yesterday, so if you, I know, but if you watch the video for the morning, you see it.
Cause in the book, it says it, yeah, in the book, it says number of moles of electrons and then parenthesis N. So I'm assuming it's the same, right? But then I don't know if.
Yeah.
Is that what you mean for number 18? It says what is N and then what is E? No.
You're right. N would be the same thing as Z.
Okay, that makes more sense. Oh, but then how would you set up your like what's your half reaction and stuff? Like what's my oxidation and what's my reducing? Because I couldn't set it up. Like I didn't know what is for this one.
This one here?
Yeah, I was having a hard time with that. I did the second number 18. That one.
Okay, what's the oxidizer?
So this one would be
What's the fuel in this case? Well, oxidizer has its origin in oxidizer. It's called oxidizer because air, we live in an oxidizing environment because air contains something that's an oxidizer. So what in air contains an oxidizer? Or what in air is an oxidizer? Oxygen. So oxygen is a very common oxidizer. So oxygen is oxidizer. There are multiple ways of figuring out what Z or N is. One is split up into half reactions. Two is to do it by oxidation states. Doing it by oxidation states is probably the easiest. So let's do it that way. We'll do it both ways if you want. So we got CH4 plus 2 O2s. This goes to CO2 plus 2 H2O. And let's just assign the oxidation states here for each element. So what are the oxidation states here? +1 for hydrogen, -4 for carbon. The carbon goes from here over to here. And so this is -2 for oxygen and +4 for carbon. And so what we see happen with carbon is carbon goes from -4 to +4. This is easy. If there were multiple carbon-containing products, this would be a lot harder. So for example, if it went to CO2, CO, soot, then we're looking at a more complex. But methane just goes to CO2, so it went from -4 to +4. How many electrons did it gain or lose?
8.
8. It lost 8 electrons. It lost 8 negative charges, so -8 electrons.
So that's because of the winner takes it all, like
That's Z.
thing, right? The winner takes it all?
Well, who's the winner in this case? Oxygen's the winner. And so how many oxygen atoms do we have? We have a total of 4 oxygen atoms. And oxygen is going to go from one oxidation state to what? And so elements in the elemental form have an oxidation state of 0. This oxygen is -2, this oxygen is -2. And so we're going to 4 oxygens with -2 as the oxidation state. So how many electrons did each oxygen gain?
4.
Plus 2 electrons, plus 2 electrons, plus 2 electrons, plus 2 electrons. So altogether, 4 oxygens will gain a total of 8 electrons. So carbon lost 8 electrons and it gave it to 4 oxygens, 2 each. And so this is a Z. Z is 8. 8 electrons lost, 8 electrons gained. Or we could split this into half reactions. If you go back to chapter 5, and look, this is a redox reaction. So we got CH4. We could split it up into 2 half reactions. We'll have the oxidation half reaction. CH4 goes to CO2. That is, we're losing electrons. CH4 is losing. Then we'll have the reduction half reaction, which is gaining electrons, which is O2 goes to H2O. Do you guys remember skeleton redox? Skeleton redox is we balance all elements other than hydrogen and oxygen. The carbons are balanced. And then we balance the oxygens. 2 oxygens here, 0 oxygens here. So we just add 2 waters. And then we balance out the hydrogens. 4 hydrogens, we need +4 pluses. And then we balance out the charge. +4, so we need +4 electrons. And so the half reaction, is that right? Oh yeah, you know what? I miscounted. I got 8 hydrogens. And so the balanced half reaction is CH4 plus 2H2O yields CO2 plus 8H plus 8 electrons. So we're gaining 8 electrons.
but for the hydrogen oxygen cell, I cannot write the half reaction because, I mean, 2H2 gas going to 2H2O. How can we balance that?
Okay, we'll take a look at that in just a second. This one, we don't have, this one is not on the chart, so we have to use the skeleton method to figure it out. This one's on the chart, so we don't even need the skeleton method. We'll just write it
Plus
out.
4H plus 4 electrons are going to 2H2O.
Right, just copy it. So this one, each O2 gains 4 electrons. Well, how many O2s do we have? We have 2 O2s, right? Because we're going to multiply this one by 2, because 8 electrons lost must mean 8 electrons consumed. So we multiply this one by 2 and add the 2 together, and we get that as the net reaction. That's using the half reaction method.
Oh wait, but never mind.
Okay. Kelly, what was your question on the balancing?
And number 53, there's a hydrogen oxygen cell. And I tried to determine the oxidation state from the half reactions, but then I couldn't.
This one?
Yes, theoretical standard voltage.
What is the theoretical standard cell voltage of each of the following voltaic cells? Hydrogen oxygen fuel cell described by equation 20.26.
Yeah.
They just want the standard cell voltage?
Yes.
Okay. So, take a look at this one, then we just add up the 2. I like to do the oxidation first. This is the anode. And so the cell voltage will equal the anode. What's happening at the anode? Hydrogen is going to water. And so hydrogen goes to water. Plus the cathode is oxygen goes to hydroxide. Oxygen goes to hydroxide. Then we go to the chart and then just take a look. For so we look for hydrogen goes to water.
And they're asking for Z too. They don't pour electrons, I just don't know how.
Okay, we'll take a look at that in a minute. Here's hydrogen going to water here. There's also hydroxide. Hydrogen goes to water, minus 0.828 volts. But since we're going backwards, it's going to be plus 0.828 volts.
Yes.
And then we look for oxygen goes to hydroxide. Here it
We're
is.
just right above.
Oxygen goes to hydroxide. It's plus 0.4. So it's plus 0.8 plus 0.4 should give you about 1.2 volts. Positive.
Oh. But they're asking for Z too. I don't know how you got 4 electrons.
Well, okay. How you get 4 electrons is, how many electrons were consumed? 4. That means we need to produce 4. And so what we have to do is we have to double this reaction and then add the 2 together so that we get 4 electrons produced and 4 electrons consumed.
Oh.
This is like the step you do in Chem 1A in chapter 5, you have to multiply this one by 2 because we got 8 electrons produced, means 8 electrons must be consumed. So that's what we do. All right, so that's the number of electrons transferred. There's Z. Any other questions?
On one of the exam, 19B, 20A, whatever, one of them, it says, what is the oxidation state of C in CH4, which we just did? Wouldn't carbon be -4?
Mm-hmm.
Because there's no option, 0 + 6 + 2 + 4.
Yeah, carbon's -4.
Should I just write it in?
Yeah, let's see. Let's see what we do.
When would carbon be +4?
In carbon dioxide.
Because that's the oxidation state.
What number was that?
4.
Oh, yeah. Okay.
Doesn't make sense.
Yeah, it doesn't make sense because none of these are right. And so there should be an E. E, which is going to be
Right.
-4. Right.
Oh, and then for number 5,
Mm-hmm.
which apparatus used to generate electricity? Is it all? I know it's A and B, right? It's A
Well, electrolytic cells don't generate, electrolytic cells use energy.
but they don't.
Yeah, you have to hook up a battery or external power supply.
Excuse me, is number 18 from chapter 19 or 20?
This is 1920.
This is 19 and 20.
Oh, because that question looks really hard.
Oh, which one? Oh, this one, 18?
Yeah.
This is from chapter 19. Yeah, I think we did this, something similar to this. Yeah. It's not that hard. But I think what happened was this problem confused people on the test because they were expecting to do an ice table, anticipating to do an ice table. But
Yeah.
it wasn't
At first
necessary.
glance, this question seems really hard.
Yeah. All right, other questions? Uh-huh.
That Z we found, is that the same Z for that formula we use in delta G equals -Z?
Mm-hmm.
Okay.
Yeah, delta G equals
2 + 4H + 4E + 2
minus Z
Is that
F
reduction or oxidation?
E.
So
So, and so this Z is, 8 over here, so this is Z. It's also called N, so in the book it switches it, interchanges it, yeah. Okay, other questions?
Yeah.
On chapter 20 stuff?
For chapter 20, so I was late on my I saw that you assigned homework and the rest for the final. So the final homework stuff, that's not tested on.
No, right. Yeah, you can ignore the that stuff for tomorrow's test, yeah.
What's the?
Corrosion and electrolytic cells. No, right.
But you want us to know.
I want you to know what?
You want us to know the type of battery, remember you said terminology?
No, I mean, on this one, I think I had. We're gonna get to electrolytic cells. Actually, we already did, didn't we?
Yeah, yesterday.
Yeah, yesterday. But you should know, voltaic cell, battery, galvanic cell are they're the same. So A, B, and C. Correct answers for that.
Electrochemistry would be all of them, right?
Yeah.
These systems.
Right. Electrochemical cell would be all of them.
Professor, what's coupled reaction? Number 10.
Coupled reactions?
will the,
That's something I forgot to talk about. Just skipped it.
It was from chapter 19.
It's from chapter 19. There's one more way to alter delta G for a reaction. And that's used a lot in metallurgy, and that is to couple the reaction. So you might have an unfavorable reaction, but you can make it favorable by coupling it with an alternate reaction. And so a coupled reaction, let's see, in electrochem would be like this. It's Hess's law, an example of Hess's law, where let's say delta G for reaction 1 is positive. And what you can do is you can add reaction 1 to reaction 2. Reaction 2, let's say, has a very negative delta G. And so that the net reaction will have a negative delta G and be spontaneous. And so an example of that would be like this. You know, if I'm looking at copper oxide solid, and I want to go to copper metal and 1/2 oxygen gas, the delta G for this is positive. But let's say I don't really care about oxygen gas. And so what I can do is I can get something to react. Let's say all I care about is the copper metal. And so one way to spontaneously form copper metal is to get something to react with oxygen that's highly favorable. And so if I take H2 plus 1/2 O2, this is highly favorable. This forms H2O, liquid, and delta G for this is very, very negative. And so if I couple these two reactions, then I can form copper metal. That is, I'll just go copper oxide solid plus hydrogen gas is going to yield copper solid plus H2O liquid. 1/2 O2's cancel. And the delta G for this will be negative. But it's not exactly the same reaction as I had before. But if I'm only interested in copper, then this will suffice. And so that's a coupled reaction. It's the last section of chapter 19. So, yeah, nobody asked me about that.
The concentration would only change delta G standard and not use delta G.
Which one are you looking at?
Number 10.
Circle all below that can potentially change delta G. Temperature, yes or no?
Pressure?
Yes. Temperature. Concentration? Yes. You know, Q, the Q term changes with concentration. Pressure? Yes, the Q term changes with pressure. Coupled reactions? Yeah, it's debatable depending on how you define it. You know, if you're looking at your original delta G.
Circle all below that can potentially change delta G naught.
And so I'd say A, B, C, and perhaps D.
I mean 11.
11?
Yes.
Circle all below that can potentially change delta G naught.
Concentrations?
Can concentration change delta G naught?
Wait, I think no, because delta G naught, it has to be 1 molar.
You're right. It cannot change delta G naught. You know, I try to use that analogy. Like if the speed limit on the 405 is 65, just can driving faster change the speed limit? No, because it's fixed. Well, delta G naught's fixed also. It's just a reference point. Mm-hmm.
is it okay if we go back to the one, number 18 we were working on? Because I was working on it, but I don't know if I got it. Because we ended up getting, our reduction was O2 plus 4H plus 4E, and it became water. And we got times that by 2 to make sure the electrons are the same. And So that means we only know our reduction, but we don't know our oxidation, right? Because there's like CH4 plus water.
Well,
Number
no.
18, and you're given your G.
You gotta determine oxidation states, the changes.
Oh, no, we got the,
No, like don't you use the formula delta G naught if you put in negative C? Like I just don't know the steps. I'm not sure if I'm doing the steps.
okay, what is E naught of the cell?
Don't you use what's his name? Something equation.
I think we do.
Yeah,
Delta G equals to ZFD.
but I got like 130 and that doesn't sound like.
So we solve for this. So then we just plug in our delta G naught's given.
Our D is given, and our F is too.
Our Z,
96,450.
our Z wasn't given, but we figured it out. What is Z?
8.
And Faraday's will be given, 96,485
No!
coulombs per mole. The moles cancel, so I'll just write coulombs. Then we got to convert this into joules. That should give you volts.
Oh, I know what I did.
Okay. Yeah, so you just plug it in and then figure out what you know this. Okay, any other questions? No. Let me finish up chapter 24. There's not a whole lot to chapter 24, what's left of it. So let's just take a look. Okay, we have three basic types of isomers. One of them is called structural isomers. The other, actually three types. There are two types of stereoisomers. Actually, there are many subtypes too. For example, ionization isomer. Ionization isomers, don't worry about that. We just call this structural isomer. In a structural isomer, you expect to see different bonding arrangements. And so here, these two have the same composition, chemical composition, but the bonds are different. And so, for example, here, the sulfate is bonded directly to chromium. Over here, sulfate is a counterion. Instead, chlorine is bonded directly. Over here, chlorine is a counterion. And so this has a different structural arrangement, different structural skeleton. So these are called structural isomers. You could subcategorize it as an ionization isomer, but nobody really uses that unless you're really specialist on this. We'll just call it structural isomer. Another type of structural isomer is like this. You know, they call this coordination isomer. Essentially, it's swapping chromium and cobalt. So this is a hexamine cobalt and a hexacyano. Actually, the parentheses are missing here. Hexacyano should have parentheses around the cyanide. Hexacyano-chromate. But over here we have the hexamine chromium and the hexacyano-cobaltate. And so, again, structural isomers because the bonds are different. This is chromium, nitrogen bonds. This is cobalt, carbon bonds. Over here we have cobalt, nitrogen bonds, chromium, carbon bonds. And so different.
What's the difference between the two?
What's the difference between the two is the ligands are different. And here, we've got a different coordination sphere of ligands. Here, it's the central metal. It's different.
But do they have the same ligands too?
They all have, well,
It's ammonia.
the thing is, the sulfate is a ligand here, sulfate is not a ligand here. Chlorine is not a ligand here, chlorine is a ligand here. And so the ligands got swapped with the anion. Okay. But anyway, they're just structural isomers because the bond or bonding arrangement is different. We have linkage isomers here. These are structural isomers also. These are just different links. For example, nitrite ion can link with a nitrogen or can link with an oxygen. And so the bonds are different here. Here we have a cobalt nitrogen bond, here we have a cobalt oxygen bond. So these are structural isomers. Structural isomers, different bonding arrangement. Okay. So we see it here. Structural isomers. Here is another set, except this is different. This, if you look, these are stereoisomers. If you look at the bonds, they're the same. We have two gray-green bonds and two gray-blue bonds. Two gray-green bonds and two gray-blue bonds. So these are not structural isomers. Structural isomers would have different bonding arrangement of the species, the same species, but different bonding arrangement.
We built this in lab yesterday. The chlorines were like opposite to one another, and the chlorines were next to each other.
Right. And so when they're next to each other, we call it cis. This is cis chloro. This is cis amine too. When they're opposite each other, we call it trans. So this is a square planar complex. I think you built the cis trans octahedral complex, right? Yesterday. And this one is biologically active. This is an anti-cancer drug. This is biologically inactive. We call these geometric isomers. Geometric isomers are going to be cis, trans, mirror, phase. And so far, there's two types of isomers we talked about. Structural, there's different bonds, and geometric, which has the same bonds but just arranged differently in space. Here's another set of cis-trans isomers. Here we have cis-chloro, here we have trans-chloro. So we got two isomers for this. COCl2 NH3 4. COCl2 NH3 4. We have the cis isomer and the trans isomer. These are these are geometric, but these are not optical isomers necessarily. Because in order to be optical isomers, there should be they should be mirror images of each other. Are they? No.
No.
And so what we do is, after we look, is there a geometric isomer, cis-trans, then we look at each one individually. Is there an optical isomer of this? And to determine if there's an optical isomer, we imagine there's a mirror here, and either draw its mirror image or build its mirror image. And so just mentally put a mirror image here, or mirror here, look at its mirror image. You'd have two amines coming this way and two chloros coming back this way. And is there a way you could flip the mirror image or twist it in any way so that it matches? And if you imagine the mirror image of this, then the mirror image is actually the exact same molecule. You could just flip it 180, up over like this, and it'll match. And therefore, we say that this is not optically active. There are no optical isomers of this. There's just one cis isomer. There's an easier way of doing that. Or maybe not. The other way of doing that is if you could slice this molecule in half. If you could slice the molecule in half and get two even halves, then we say it's not optically active. If you can slice, if it's impossible to slice this in half so that you get two even halves, then it's going to be optically active. There should be an optical isomer for this. And so here we could slice it in two ways and get two even halves. We could slice it like this, or we could slice it like this, between the two chloros and the two amines. and then it splits up into two equivalent halves. For the trans isomer, we can ask ourselves, is this isomer optically active? Does this have an enantiomer? Well, we could draw a mirror here and draw its mirror image, or we can see if we can slice it in half. Is there a way to slice this in half? Yeah, there are three ways. You know, we could slice it, and we got to imagine cutting the atoms in half. We slice it in half this way, and so we get two equal halves, or we slice it in half this way, or we can slice it in half, you know, along the horizontal plane. And so the trans isomer is not optically active, and so there are only two isomers for this compound, and that would be the cis and the trans. Those are geometric isomers.
How come the trans is not optically active? And
Because-
these two even have.
Its mirror image is exactly the same, you know.